So we're going to finish up section 5.4. We did part 1 yesterday, a lot of drawing vectors. Today we're still going to do drawing, but only if it's a word problem. Okay, for everything else, we're going to try to figure out a way to add vectors and subtract them without making a sketch. So first thing we're going to look at is what it means for two vectors to be equal. Okay, for two vectors to be equal. So suppose I have two vectors. Okay, I'm calling them v and w. Remember, vectors should either look bold or you could put a line on top. Okay, if you've looked through your book at all, they use bold letters. All right, so two vectors are equal, basically, as long as the horizontal components match and the vertical components match. That's what makes two vectors equal. So let me draw two vectors that are equal and show you what happens. Let's do it down here. Let's pick a vector. Let's do I don't know, 3, 5. Remember, make sure you put the angled brackets if it's a vector. Don't use parentheses. Okay, so 3, 5 would look like this. 1, 2, 3, 5. Yeah. Let me do another one over here. 3, 5. Okay. According to my definition, are those two vectors the same? Yes. Yeah. Are they drawn in the same spot? No. That's the key. Some people think that for vectors to be the same, they have to start at the same spot and end at the same spot. No. They just have to, if you move them to the same spot, then they would look the same. Okay? But they can start and end at different spots. So those vectors are equal. Yep. Okay. So another way to think of it is once you make a triangle out of it, bottom side is 3, height is 5. If the other vector makes the same triangle, then it's equal. Bottom side is 3, height is 5. Yep, same vector. Same length, same direction. All right. So the last way I'm going to show you how to write a vector is called unit vector notation. So we've done the drawing, that's one way. We've done the brackets, that was the second way. This is going to be the third way. We're going to stick with this way or the brackets. Okay? Unless it's a word problem, we're not going to sketch it. So can someone remind me again, what does it mean if a vector is a unit vector? There's something special about it. Yeah.
It has a magnitude of 1.
Yeah, it has a magnitude of 1. And remember, magnitude means length. We had some trouble with that in the first class. Magnitude is just the length of the vector. If you draw it on paper, how long is it? That's it, magnitude. So I'm going to define two special unit vectors right now. Okay? So these are special names that you give to vectors, and you would never use this name for a vector that you draw, because this name, it's like reserved, it's special. Right? So you never use this name that I'm about to show you for anything other than this. The first vector is I. So when you call a vector I, you're using that's a special name. The vector I always means it's a unit vector that points to the right. Always. Has nothing to do with imaginary numbers. So the vector I, it's just a vector that points one unit to the right. Okay, and if you wanted to see a picture of it, it looks something like this. There's I. That's it. Just a vector, points one unit to the right. Okay. The other vector that has a special name we're going to look at is J. It's a unit vector, and it points up. So it's a unit vector, it's 1 unit long, and it points up. And the idea is what we're going to do is we're going to think of I and J as like building blocks, or like Legos, right? We're going to stack them together to make a vector. Just like we did this yesterday. We would connect vectors together, and then the final answer was always like that diagonal. Well, we're going to do the same thing. We're going to stack I's together like that, and we're going to stack J's together like that to build a vector. It's just a matter of how many I's and J's that we need. Okay. So we're going to use I and J to build vectors. That's what I just said. All right, so here's a picture of I again. It's 1 unit long, it points right. Here's J. 1 unit long, it points up. So I'm going to give you a vector. I'm just going to make one up. Let's do the vector 3, 4. Okay. So the vector 3, 4. If I start at the origin, 3 tells me that I would go 3 units which way? 3 to the
right.
Yep, 3 to the right. And then the 4 tells me how many units to go up. So 3 right, 4 up. So 3, 4. Now, what I want to do is try to build that vector out of I's and J's. And this is going to give me another way to write the name of it. Let's make this a different color. Okay. If I'm trying to get from the initial point to the terminal point, how many I's would I need to stack together? Olivia?
3.
3, yep. So I'm just going to make 3 copies of it. 1. It's probably quicker if I just draw them by hand, but 2, 3. All right. So I just put 3 of the I's all added up. So 3 I plus, I'm not done yet. I'm going to put some more on the end of that. There's arrowheads on them, but it's kind of hard to see. If I zoom in, I don't know. Okay. How many J's am I going to need? Starting from where I ended with the green ones to get up. How many? 4. So I'm going to make, you know what? I'm just going to draw it because it's quicker. I'm going to put 4 J's. 1, 2, 3, 4. So I have 3 of the I's plus 4 of the J's. And that's another way to write the vector 3, 4. 3I plus 4J. That's it. That's all there is to it. So if you have something written like this and you want to turn it into I's and J's, all you really have to do is take out the comma and the brackets and put in an I and a J with a plus sign in the middle. That's all you really end up doing.
Are there like special vectors for like the ones that go in the other directions, or do you just do negatives in front of I and J?
You just do negatives, yep. That's what I was going to mention next. So if you wanted to get over here, I points right, J points up. Well, that one's left. So what would you have to do in that case? Negative I. So in that case, it would be negative 1, 2, 3, 4, 5, 6, negative 7I plus 3J. So together, using I and J and making them positive and negative, you can get to any coordinate on that grid. You can get anywhere you want to go. So the fancy word for being able to get wherever you want to go is span, S-P-A-N. Vectors I and J span 2-dimensional space. Okay, you can go anywhere. If you didn't have J, what would you be limited to? if you didn't have j, say I got rid of j, you could only move which way?
Left and right.
You could only go left and right. You could go anywhere you want on the x-axis, but you'd be stuck in one dimension. You'd be stuck on a line. Once you add in another vector, you can go in 2 dimensions. Well, if you wanted to go into 3 dimensions, you would need to add one more vector. I and j could move you left and right, up and down, and then the third one we would call k could move you in and out of the board. There would be your 3D. Okay? But we only need 2 vectors because we're only doing 2 dimensions right now. Any questions on how we did that? Okay. So let's look at some of the stuff we did yesterday, like adding, subtracting, and scaling vectors. But this time we're not going to draw anything. We're just going to do all numeric calculations. So to do these calculations, I'm going to give you 2 vectors, but I'm not going to draw them. Okay? They're just going to be represented with numbers. When we do an actual problem, it's going to be like that. Those are going to be your vectors. No pictures at all. V and W are going to be the vectors, and then alpha is a scalar. Okay, so remember, a scalar, that's just a number you put in front of a vector, and when you scale it, 3 things can happen. It can get longer, it can get shorter. What's the third thing that can happen when you scale it? Matt?
It could reverse, it could go the other direction.
Right, if it's a negative scalar, it flips around and points the other way. Okay, so this would be a number. These other 2 things, these should be bold because they're vectors. Okay, so there's your first vector. Again, in a real problem, x1 and y1 will be numbers. Just like this, like 2, 3.
What's the M for is?
Alpha? Yeah, it's just the Greek letter alpha. It's what your book uses to represent a scalar. So alpha should look more like this. If I draw it really nice. Kind of looks the same, I guess. Right. So our first vector has an x and y coordinate. And W, second vector, it has an x and y component, not coordinate, component. Okay, let's look at how we would add these vectors up. So if we wanted to add them the old way, you would take V, you would draw it, you would take W, draw it on the end of V, and then you'd connect the diagonal. That's how you add them visually. Well, if you want to add them but you don't want to draw it, all you have to do is add the horizontal components, comma, and then add the vertical components. And doing this is exactly what we do in that picture, except we're not drawing it. Subtraction works pretty much the same way. With subtraction, drawing is even more of a pain, because then you have to draw a vector, then you have to take the one you want to subtract, flip it around, and then put it on the end. Well, all we have to do to subtract them is subtract the horizontal components and subtract the vertical components. Now, when you subtract, does order matter? Yes. So V minus W means take the V component and then subtract the W component. X1 minus X2, not X2 minus X1. That's the other way around. Okay. So the next thing we're going to look at is scaling a vector. So it could be like 2V or negative 1/3 V, okay, something like that. But alpha would be a number. That's a vector. Okay, when you want to scale a vector, normally what you'd have to do is if you had the vector, and say you want to do 3 of them, then you got to connect 3 of them on paper, like this. And then your final answer, would be the whole line, the whole arrow. Well, without drawing it, all you have to do is multiply each component of the vector by what you're scaling by. multiply the horizontal by what you're scaling by, and the vertical by what you're scaling by. Okay, we're going to go through, I'll give you some numbers next. We're going to do one of each. And then the last thing is this. What do those double bars mean? That's a vector inside the double bars.
It's the magnitude.
It's the magnitude, which, what does that really mean again?
The length.
It's just the length. So think about if you had a vector. Let's just put this right here, like this. How could you find the length of that vector, like if that was your piece of paper? Without like a ruler, just using a calculation. Any thoughts? You might have to draw a little bit more in there, but there's something you could do to get that. Yep.
You could make it into a triangle and then use trig, like the Pythagorean Theorem.
Yeah. So just go like this. And now 2 of those sides are very easy to measure. 1, 2, 3, 4, 5. 1, 2, 3. I have 2 out of 3 of the sides. I can find the third side using the Pythagorean theorem. So it's the horizontal component squared plus the vertical component squared, and then take the square root. That's the Pythagorean theorem. And that's what I have right there. Take your horizontal component, square it. Vertical component, square it. Add them up, and take the square root. Okay, so let's try. We'll try one of each. So here's our vectors. I've written them in what we call unit vector notation, that's i's and j's, and the algebraic notation, that's with the angle brackets. We'll practice writing our answers both ways. You should be able to do either one. First one I want to do is v plus w. So the DJ, in the first vector, v, what's the horizontal component?
2.
2? And what's the vertical? What's the horizontal component in w?
In W, 3.
3. So we're going to take a horizontal of 2, a horizontal of 3. We're going to add them up, and we get a horizontal component of how much? 5. And what do we put next to it, just so somebody knows it's horizontal?
I.
I. So you get 5i. And what about the vertical? Get the vertical in v, look at the vertical in w, add them together. Yep.
-1j.
Yep. You have 3 plus a -4, that's -1j. You can also just put this. You can just put -j, that's fine too. Now, what if I wanted to write it this way? It would be what, comma what, if I did it that way. Tristan?
It'd be 5, comma, -1.
5, comma, -1. Yep. I would accept either answer if the directions didn't say. If the directions say unit vector, then I want i's and j's. If it says algebraic, then that means angle brackets. That's just what they call that one. Okay, let's look at v minus w. Same idea. This time we're just subtracting. Okay, if I subtract, I got to make sure I get the order right. So Wally, when I subtract v minus w, what's the number with I going to be? So first, what's your horizontal in v again? What? Not I. I'm looking for the actual number. what is the length of the horizontal part of V? 2. And what's the length of the horizontal part of W? And now subtract those two. -1. That's what you get when you do V minus W. So -1, just make sure we put the I with it. So if you want to put -1i, that's fine. -I works. And now be careful here. What's the vertical? It's -I, yep.
7.
7, right? It's 3 minus -4. It's 3 plus 4. 7j. So we got that. Or -1, 7. Either way. Okay, let's look at C. This is just an operation on one vector. You're not using W. You're just going to take V and triple it. So take vector V and triple. Okay. So what would, if you take V and you triple it, what would that turn into? Just think of it as like a distributive property. Okay?
6i plus 9j. Sorry.
Yep, 6i plus 9j. Or 6, comma 9 brackets. Okay, and the last one we're going to find is the magnitude of V. Okay, magnitude. Let's go back and look. It's the square root of each component squared. And then you add them up. So let's fill in everything we can before we put numbers. We've got a square root. We're going to add two things after we square them. So for vector V, what's the first number that I'm going to square? Oh, Kelsey?
2.
2. What's the second number?
3.
3. So 2, 3. Nick, what's 2 squared?
4.
And 3 squared?
9.
9. So we add those up. And the exact answer is the square root of 13. The approximate answer is about 3.61. And that's how you find the magnitude. All right, so take a look at A, B, C, and D. Out of all 4 of those, which one, when you look at the answers, which one looks different than all the rest? Olivia?
D.
D. And that's because D is not a vector. The answer to A is a new vector. The answer to B was a new vector. The answer to C was a new vector, 3 times as big. The answer to D is a number. It's just a length. Okay? So A, B, and C all had vector answers. D is just a number. Questions on that? Okay. So next thing we're going to look at, and then we'll do the 2 word problems, and that's it. So the next thing is basically how can we turn a vector that's not a unit vector into a unit vector. So pretend like you had the vector in black, okay, and it's too big. The vector in red represents a unit vector. So what we want to figure out is how can you take something that's too long and shorten it to make it exactly 1 unit long. Or you could have the opposite problem. You could take something that's too short and lengthen it. But the goal is you want to end up with something 1 unit long. So let's see if we can figure out the formula to do that. Let's say you had, yeah?
I was wondering, would you use kind of division?
Yeah, you can use division or multiplication, depends on how you think of that. But yep. Let's say you had a vector that was 5 units long. What would you have to scale it by to make it 1 unit?
1/5.
1 over 5. So the length was 5. He scaled it by 1 over 5. What if you had a vector that was 8 units long? What would you scale it by to make it 1 unit? Yep.
1.
1 over 8. It was 8 units. You scaled it by 1 over 8. What if it was v units? What would you scale it by? If you had a vector that was v units long. Yep. 1 over v. So if you have a vector and you scale it means to multiply it. You scale it by 1 over its length. If it was 10, it was 1 over 10. If it was 8, it was 1 over 8. If it was v, it was 1 over the length of v. If you take a vector and multiply by 1 over its length, that will always give you a unit vector. And I think I have that written down below. So actually, I'll just go like this. Yeah, right here. So now Shelby said, could you use division? Yeah, if you do this out, it really is just division. Think of it as a fraction. V times 1 in the top, 1 times magnitude in the bottom. So whether you multiply by 1 over the length or just divide by the length, it really means exactly the same thing. Right? So here's the formula to convert a vector into a unit vector. All it's doing is it's changing how long or short it is to make it exactly 1. It's not changing the direction. Okay? So first thing you have to figure out when you're converting something to a unit vector is how long is the vector they gave you? Is it 5 units long? Is it 6 units long? How long is it? And then once you know that, you can fill that number in right there. Okay, so new vector points the same way. It's 1 unit long. Okay, let's try an example. So we've got the vector 3i minus 4j. I want to find a vector that points exactly the same way as that one, but I only want it to be 1 unit long. So let's figure out how long this one is first. If it's already 1 unit long, then we don't have anything to do. If it's not, then we have to fix it. Okay. So when I want to find the magnitude, what should I write down first so I don't forget it? Before I write any numbers, it's part of the formula. Okay? Yeah, just put the square root, because some people do all the work and then they forget to take the square root at the end. So if you write it right away, then you probably won't forget. Plus, and then we're going to square 2 things. Dan, what's the first thing that I'm going to square? 3. And what's the second thing? Yep. Doesn't really matter if you square the -4 or +4, it's all going to come out the same. All right. 3 squared is 9, -4 squared is 16. What's 9 plus 16? 25. So that means this vector is 5 units long. So what are we going to end up scaling each component by to shorten it? You could either say we're going to divide by this number or it's multiply by this number. It's 2 different ways of saying it. Elise?
1/5.
You're going to multiply everything by 1/5, which is really just dividing everything by 5. So our unit vector would equal, let's just write it this way. What would be the horizontal component? Originally it was 3. We're going to scale it by 1/5. What do you got? Now? Yep, you get 3/5. Now your vertical component was -4. You're going to scale it by 1/5. What's that one going to be? That's it. So all you had to do was scale everything by 1/5. That vector points the same way. It's just 5 times shorter, and it makes it 1 unit long. Any questions on that one? All right, so last two things we're going to look at are the word problems. The first one, once we figure out what the formula is, that one's very, very easy. The second one, it's a little bit harder. So we've talked about using vectors to represent two things. Velocity, that's an object like an airplane moving in a certain direction at a certain speed. And we've also talked about vectors to represent force, how hard you're pushing or pulling on something, and in what direction you're pushing or pulling. We're going to do a force problem next. We're going to stick with a velocity problem for the first one. Now, if I were to throw an object, right? I throw something, what's going to control how far it goes? There's really two things. How hard I throw it, which is usually measured in the speed. So the speed at which I throw it. And what else is going to control how far it goes? Yep.
The angle.
Yeah, the angle. I mean, if I throw it straight up, it's not going to go anywhere. It's just going to come right back down. If I throw it somewhere in between straight up and horizontal, there's some optimum angle there to make it go as far as I need it to go. So those are the two things we're going to look at. And together, those two things are going to make up a velocity vector. So let's pretend that that's how we threw an object. Okay. If you threw something like that, what direction is that arrow pointing? Yep. So this object is traveling to the right. Is it traveling any other way? Up. So you've thrown something up and to the right. So what I want to do is I want to visualize up and right separate. The way I do that is I make a triangle. Try to draw this straight down. That arrow in red represents the right part. Okay. This arrow in green represents the up part. If you combine the red and the green, just like we learned yesterday, and draw the diagonal, there's the effect of the red and the green at the same time. That'd be your throw. All right. Any questions so far? Now, someone earlier said we throw it at a certain angle. So let's call our angle alpha. So if this was like a cannon or like a piece of artillery, you probably could set the angle, whatever angle you want to achieve whatever you're trying to do. Now, the other thing I want to do is let's call this x, because that's going to be my horizontal, and let's call the green one y. Okay, so I just gave names to the red and the green vector. All right. What I want to do is basically come up with this formula. I want to figure out what is x and what is y. And that's going to be my velocity vector. I just have to figure out x and y in terms of the angle I'm throwing the object at and how hard I'm throwing the object. Those are the two things I want to have in my formula, for x and for y. All right, so let's look at it like it's a right triangle. I'm going to circle this, this, and that. The side that I've labeled x, okay, the side in red, what's the name of that side? From the perspective of alpha. The choices are opposite, adjacent, or hypotenuse. So,
It's the adjacent.
it's adjacent. What's the side that's labeled v? Is it opposite? Well, we already did adjacent. So is it opposite or hypotenuse? Please?
Hypotenuse.
It's hypotenuse. So I'm trying to find a trig function that involves adjacent and hypotenuse. And that's how I'm going to represent x. What trig function involves adjacent and hypotenuse?
Cosine.
Cosine. So let's set up a formula for x. The cosine of my angle equals adjacent over hypotenuse. There's the adjacent. Now, when I say over hypotenuse, what do I mean? What about the hypotenuse? Over the color of the hypotenuse? over the weight of the hypotenuse, over the hypotenuse's favorite food. Like, what do we mean? Like, what about the hypotenuse? Yep.
You need its magnitude.
Its magnitude. We need its length. So the cosine of alpha is the adjacent, length of the adjacent over length of the hypotenuse. That's why I put these bars around it. Now, how would I move the magnitude of v to the other side and get x by itself? Just multiply by?
The magnitude of v on both sides.
Yeah. Multiply by the magnitude of v. That's gone. Magnitude of v. And there's how you write x. It's how hard you throw it times the cosine of the angle that you throw it at. Okay, so there's your x. Now we do the same thing for y, except y is opposite. Opposite hypotenuse. Which trig function has opposite and hypotenuse in it? And it's not cosine. Show?
Sine.
Sine. So sine is opposite over hypotenuse. So let's set it up again. Sine of, what's my angle again? Yeah, Tyler? Yeah, my angle's still alpha. We haven't changed that. Equals opposite over hypotenuse. What am I going to put on the other side? Fraction of what over what? Okay?
Y over the, what it's called. So 2 lines, v, 2 lines.
Yep, magnitude of v.
Magnitude.
And then get y by itself, just like you did before. All right, and sine alpha. There's your formula for y. So now we can fill that in, and we can write our velocity vector. In fact, we can write it 2 ways. We can write it with i's and j's, or we can write it with the angle brackets. Let's do both. So it's x comma y. There's your x, comma, and then copy down your y. Now, if you wanted to write it with i's and j's, which one of these is the I? The first one or the second one? Erica? The first one. So you just put this number down, whatever it happens to be. Usually you need a calculator to find it. So you'd have a number in front of I, plus, and then your second one, sine alpha, and that's in front of j. Now, if you look at that, both of those have something in common. Anytime you've got a plus or a minus sign and you've written the same thing in 2 spots, we can pull it out in front and just write it in 1 spot. Kind of like if you had this, and you learn in algebra, you can factor out an x and just write it like that. We can do the same thing here. Does anybody see what I can factor out from both of them? Pat?
Is it the magnitude?
Yeah. You don't have to, but it just makes it so you only have to write it 1 time, and that's how your book does it. So we can put the magnitude in front of everything. If I take it out of the first one, I'm just left with cosine alpha I. If I take it out of the second one, it's already in front. I'm left with sine alpha j. there's the formula we can use for a velocity vector. So there's two things they have to tell you in the problem. One, how fast is the object being thrown, launched, projected, whatever. What's the angle that it's being projected at? And I think I had the same thing. So yeah, if you're given an initial speed and an angle, use the following formula. It's the formula I just gave you. Okay, so you don't need to write that. It's the same thing. We just wrote it. Any questions on the formula? So now that we know the formula, it's very easy to use. You just plug two numbers into it, and that's it. The calculator does the rest. I think I already said that. Alpha is your angle. Magnitude is how hard you throw it. So if you want to write that, you can, but that's what they are. Okay. So it says we've got an object being thrown at 50 miles an hour at an angle of 30 degrees. Find the velocity vector. And then after we find it, I just want to know what each number means. Okay, so when I write a velocity vector, what's the first thing you write down? What's out in front of everything? Oh, Nick? It's what we just factored out.
The trig function?
The trig functions are going to be inside the parentheses, but there's something out in front of the parentheses. Yep.
The magnitude.
The magnitude. Yep. And what's the magnitude here? We've got two choices. One of them's the magnitude, and one of them is not. Yeah.
50 miles per hour.
50 miles an hour. So put the magnitude out in front, and then cosine alpha I, sine alpha j. But fill in alpha. What's alpha in this case? 30. So cosine 30 I, we need to do that out, plus sine 30 j. Okay. Because I have the 50 on the outside of parentheses, what property is that going to be? Yep, distributive. So just distribute it. Okay. So 50 cosine 30, but I got to be careful because I am not set up right. What do I have to change?
Radians to degrees.
I got to change to degrees. So I get 43.3 I. 3.3 I plus, if you just trust me, it's going to be 25J. Just type in sine 30 and multiply by 50. That's what you. Or don't trust me and try it yourself. All right. So there's your velocity vector. But the next part says, what do each of these numbers mean? Well, what's the number with I? What does that mean? The number with I is your what? Okay?
Direction it's going in right? Or would it be like the force?
Not the force, but the... What are we measuring in this problem? We're not measuring force.
Velocity.
We're measuring velocity, speed. So if I was standing right in front of you, right, and you threw this towards me, and I had a radar gun pointed straight at the object coming at me, it would say this object is coming at me at 43.3 miles an hour. Now, you might be like, well, yeah, but I threw it at 50. Yeah, but you didn't throw it straight at me. You threw it up a little bit. So part of your energy went into throwing it up, and then part of your energy, most of it, went into throwing it forward. So this is the speed in the horizontal. So that, what does that mean the 25 would be? Speed in the vertical. So if I was above this situation, you were throwing an object and I was above it, maybe on top of like a building or something, and I pointed a radar gun straight down at the ball as you threw it, the radar gun would say it's going 25 miles an hour. It would see it coming up at the radar gun at 25 miles an hour. That's the speed in the vertical. Now, that's only the speed the second it leaves your hand. Because once that object leaves your hand, it's slowing down the whole time. Right? It slows down until it hits its highest point, and it comes back down. The horizontal speed doesn't really change. The only thing that would change that is air resistance. Okay? But if you're throwing something like a baseball, I mean, that's air resistance isn't as, I mean, it has an effect on it, but it's not a huge effect. If you've got a piece of paper, and you're trying to have a piece of paper and you throw it, but keep it flat, it doesn't, there you go.
Thanks.
It doesn't go very far. I need that back. So when you throw a piece of paper, it just kind of, the wind slows it down a lot. But a baseball, if I had that and I drop it, it's not going to affect it as much. Did you need that?
It does not sound good. You can keep it.
You sure? Okay. So any questions on that? All right. So that's all you've got to do for a velocity problem. Plug in your speed, plug in your angle, do it out. There's your answer. Okay. Last problem. Homework's only one slide away. That's the good part. So the last problem is about static equilibrium. Static means things aren't moving. It means things are staying still. Equilibrium means balanced. Right? So if you look at all the objects on this table, including the table itself, this table is static. It's not dynamic. It's static. It's not moving. Equilibrium. The reason it's not moving is because everything is balanced. This book is pushing down on the table. Why doesn't it fall? Because there's something else pushing up, holding it up. So the force of the book pushing down and the force of the table pushing up against it are equal. If they weren't, this book would either be falling or rising up to the ceiling, right? But the forces are balanced, right? So that's what it means to be in static equilibrium. Nothing's moving because everything is balanced. Things become unbalanced, they move. So what we're basically going to look at is we got an object hanging from a ceiling with two cables. The goal is I want to find out how much tension is in each cable. Right, so let me show you the picture. Make it a little smaller. Okay, so it looks like that. Two things make this a little complicated. One is the cables are different lengths. They're not the same length cable. One's longer than the other. Two, the cables are anchored at a central point on the object, making the cables go at angles. If the cables went straight up and down, the cables in the lights, if the lights weighed 100 pounds, and there's 1, 2, 3, 4, 5 cables, each cable would be holding 20 pounds, assuming that the weight is distributed evenly in the lights. And I know the end cable's a little closer, but whatever. But these cables aren't straight. They come off at angles. So if you were to all of a sudden cut that cable, what would happen? If that cable broke, it would swing, right? It would swing which way? It would swing to the right because the force just became unbalanced. So that means that this cable must be pulling it which way to hold it where it is? It must be pulling it left. And is the weight falling to the ground right now? No, but it must also be pulling it up. So this cable is pulling that way. It's pulling up, but it's also pulling left. Same deal with this cable. If you were to cut this cable on the right, the weight would swing to the left. So this cable is pulling it right, and it's pulling up. What I want to do is what we did right here. I want to break everything down into left and right. That's kind of my goal. So to break it down into left and right, I have to draw what shape? I need triangles. So the first thing I'm going to do is I'm going to put a horizontal. I'm going to put it. I'm gonna win. Oh, I'll switch fingers. That one will work. I don't know why. So I'm gonna put a horizontal in right there. Next thing I need is 2 verticals. Not here. I'm gonna move it after, as long as I can move it. I'm gonna put 1. I'll put it up there. It's longer than I need it, but that's fine. 1 there, and 1 there. So, how many right triangles do I have now? 2. 1, 2. Now, if I'm going to work with those triangles, I really need angles. I don't have any angles in these 2 triangles. How much is this angle right here? It's 60, which means this angle at the bottom is 30, because they all add up to 180. How much is this angle right here? Yeah, this triangle on the right is a 45, 45, 90. So 45, 45, 90. So at least I've got everything labeled. Now, let's call this cable, I'll call it the tension in cable 1. I just want to have a name for it. And the tension in cable 2. Now, because I made triangles, I can do what I did right there. I can make those red and green arrows. Right? Let's make the green arrows the horizontals. That visually represents cable 1 pulling left. This is cable 2 pulling right. Right? And what I do in red, that's going to represent up. This represents cable 1 pulling up, cable 2 pulling up. Now, why is the object moving? What did I say? Because everything's what? Everything's balanced. So that means the forces pulling up and down are the same. The forces pulling left and right are the same. So let's give names to those green and red arrows, and then we can write down what we just said, that it's balanced. Let's call this one X, because it's horizontal. We'll call it X1. This one we'll call X2. Okay, they're both X's because they're horizontal. What would be a good letter to use to name the red arrows? Y. So let's use Y1 and Y2. Y1, Y2. Okay, so what's the force here that's pulling left? There's only one arrow in this whole picture that points left. I mean directly left. X1. Right. So the force pulling left is balanced by the force pulling which way? Right. What's the name of the force pulling right? There's only one. X2. Right. So in a minute, we just have to figure out what is X1 and X2 in terms of that angle and the hypotenuse. So we're going to use sine and cosine, just like we did with velocity. All right, so that's good. That's left and right. What about force up? What's the force pulling up in this picture? Y1 and Y2 working together. So Y1 plus Y2. And what's the force that's pulling down? What wants to fall to the floor? 1,200 pounds. Okay, so that's the only number that we have so far. But this is what we have to work with. Okay? Any questions on setting that up? All of this is exactly the same in every single one of these problems. The only thing I've done specific to this problem so far is I put in 1,200. The 1,200 could change. It could be 800. It could be 900. That could be different. But all of this is always the same, what I just circled. Now, let's write down what these all are in terms of angles. Once you do one or two of them, you kind of start to see a pattern. You're not going to have to probably do it 4 times. Let's start with x1. I'm going to look at it from the 30-degree angle. That's my perspective. What side is x1? Opposite, adjacent, or hypotenuse? Adjacent. What side is t1? Hypotenuse. Which trig function involves adjacent and hypotenuse? Yep, Nick.
Cosine.
Exactly, cosine. So off to the side, I'm going to write down cosine of my angle equals adjacent over hypotenuse. x1 over t1. Now, how would I get x1 by itself? Multiply by t1 on both sides. t1 cosine 30. There's your formula for x1. Let's do x2. Anyone think they know what x2 would be? Kind of following the same pattern without going through all the steps? Follow the same pattern, and it's still horizontal, so it's still a cosine, but it's not. It's a different angle, and it's a different t. Yep.
T2 cosine 45.
Yep. Just follow the pattern. All right. x1, x2. We have 2 things we can fill in. Yeah, just say no. Let me do one y1, and then I think we'll be able to do the other y2 the same way. What side is that from the perspective of the 30? Yep.
Opposite.
Opposite and hypotenuse. Which trig function is that? Yep.
Sine.
Sine. Yep. So let's set that one up. It's going to look very similar, except cosine is going to be sine. That's the only difference. Sine is opposite over hypotenuse. y1 over t1. Okay, so what's y1? Yeah.
It's going to be t1 sine 30.
T1 sine 30. Now, without going through the whole thing again, does anyone think they can tell me what y2 would be? Yep.
T2 sine 45.
Perfect. There's y2. Now, at this point, we've done all the hard stuff. We've done all the trig. We've done kind of the physics idea that force left equals force right, force up equals force down. All we have to do is plug in those 4 boxes into these 4 spots. It'd be nice to get decimals to these numbers at this point, too. So we'll get decimals, and then we'll have a system that we can solve using Algebra 1. All right? But all the hard stuff is done. Now we just type it all in and use some algebra. x1, t1 cosine 30. Okay, let's round it off. Cosine of 30, 0.866. So that's 0.866 t1. 0.866 t1 equals x2, cosine of 45. Let's see what that is. 0.707. So 0.707 t2. That's x2. 707 t2. There's your first equation that you're going to solve. Remember I said don't get confused because there's decimals. There's going to be decimals. Second equation. y1. y1 is t1 sine 30. Oh, let's look at the sine of 30. 0.5. So it's 0.5 t1. So 0.5 t1 plus y2. Y2 is T2 sine 45. I already know the sine of 45. It's 0.707. It's the same number we just got up there. So that's y2. And let's go back up. What's that equal to? 1200. So now all the trig stuff is done, the physics stuff is done. You have to solve that. So what did we say when we solve a system? The method that we use. Anyone remember the name I gave it? Begins with an S. Substitution. Which one of those equations do you think it's easier to get T1 or T2 by itself? Probably the first one. Doesn't really matter. Let's get T1 by itself. How could you put 0.866 on the other side? Divide. Divide by 0.866. Divide by 0.866. That's gone. So T1, I'll do that out, is 0.707 divided by 0.866 with a T2 next to it. So where am I going to plug that in for what letter? For T1. Okay, so let's plug that in, and then we're just going to have a bunch of decimals we have to multiply out. 0.5 times, let's do that. 707 divided by 0.866, 0.816. That's that part. Now, copy down the rest. Someone with a calculator, could you just tell me what 0.816 times 0.5 is? 0.408? Yeah, I'm sure that's right. 0.408.
Yeah.
The next one I can't do in my head though. I have 0.408 T2 plus 0.707 T2. What can I do with those? Combine them. What's 0.408 plus 0.707? Point 1.115.
Yes.
And now I'm one step away from the tension in cable 2. Divide by what? Yep. And if you can get the tension in cable 2, that's good enough. Don't worry about the tension in cable 1. So what is the tension in the second cable? It's less than 1200. I don't know what. Yep.
1076.23.
1076.23.
That's approximate.
Roughly, okay. If you can get that tension, that's good. Okay. So that word problem, that one's challenging. It's not an easy one. It's a tough one. The velocity one, that one I hope was a little easier than this one. But that's a tough one. So homework tonight, page 344 on 25 to 47, just the odds, 55, 57, and 66.